Hello, I'm Pam Hoffman, Everyday Spacer.
I'm Jeff Miller, 2049 Outfitters.
At Everyday Spacer, we show regular folks how to personally and directly participate in space exploration, science, and astronomy. We're here on Friday nights at 9 p.m. Pacific Time, 12 midnight Eastern Time, and 6 a.m. on Saturday in Germany. We're broadcasting live from Thousand Oaks, California.
Tonight's guest is Dr. Greg Hodgin, and we'll be back in 8.3 seconds. And first comment. Hi, Janie.
Hi, Janie.
Yeah,
welcome.
It is chilly unless anyone's in the Midwest and they're about to thump you.
Yeah.
But
oh, somebody else.
Speaking of, hi,
welcome, Dawn. They might have snow. I don't know.
Yeah. So
I haven't heard lately.
Greg Hodgin, Ph.D., is the CEO of ZC Institute, a fusion startup that is engaging in quantum spacetime distortion research to create microfusion reactors, turning sci-fi into reality one bubble at a time.
Dr. Hodgin served as the executive director and founder of Peacebuilding Solutions, a nonprofit dedicated to the rights of forcibly displaced persons. He graduated from Emory University with a bachelor's in chemistry and from Georgia State University with a bachelor's in history and master's in political science, along with a Ph.D. in political science. That's 2 bachelor's and a master's degree and a Ph.D. Yep. Go ahead.
Okay, and just right up, Scott.
Oh, hello, Scott. Welcome.
And Cliff. Hey, Cliff.
Hey, Cliff. The usual suspects are here now, Greg.
Yeah. Hodgin has tussled with Russians at the United Nations and won. I'm assuming if it's at the UN, that was verbally. Defended and expounded refugee and IDP rights on the floor of the UN on 2 continents. He has also had 2 machetes and an AK-47 shoved in his face while doing field work. Yeah. And he's an avid gamer, which helps sharpen his diplomatic skill set.
Thanks for joining us, Greg. Tell us more about your new venture after we take another comment here. What do we got? I saw Scott.
Oh, Scott says, I love his green screen. That is amazing.
It is.
Oh, thank you. Isn't it lovely? Yeah.
And we got somebody new. Welcome, Kyle Van Doyle.
Yeah.
Van Doyle.
Hello, fellow beings having a human experience.
Okay. Excellent.
And Cliff. Yeah, how did Craig get my lunch?
All right, Greg.
It was a garage sale.
Yeah. Let's turn it over to you, Greg, and we'll continue to watch for questions.
Absolutely fantastic. So let me go ahead and share my screen real quickly, and then I will go ahead and get started. First of all, thank you both, Pam and Jeff, for allowing me to come on tonight. I really appreciate it. We're going to have some fun with this, and let's go ahead and share that and get started on that. There we go. So what we're doing at ZC Institute, we're actually putting a lot of researchers together to figure out something that a lot of science has been looking at for the past 20, 30, 40 years. And only in the last few years has it actually become possible. But first, let's talk about why it was so hard in the first place. One of the issues we see with trying to figure out faster than light travel is the fact that a lot of the math that we're discussing with respect to warp drives and the warp drive literature discusses the fact that you need what's called exotic matter. So that's negative matter, negative energy. And when people hear negative matter, negative energy, they kind of think, what is that? And the answer is, let's say you have, I don't know, a bank account that has positive money in it, and then someone gives you a bill, which is negative money, and the money goes away, right? There's not an explosion of money or weird things like that. It just disappears. This is the same thing. Negative energy and positive energy cancel each other out. Negative energy, negative matter and positive matter cancel each other out. We don't know if this even exists or not. We think that there might be some way to produce it, but we're not there yet. And even if we did, we don't have a way to really produce the sufficient amounts with our current technology to even take a shot at anything of this nature. So the power requirements are way too high for us to do any kind of faster than light travel with warp drive or even to do something of that nature. If you have a warp field about the size of 100 meters, which is about what the Enterprise would use on Star Trek, you would need, according to the most recent math, about the mass energy of Jupiter. That doesn't sound like a lot, but well, Jupiter's pretty big, so we can't really do it anytime soon, right?
Yeah.
So the joke that we usually talk about is that, in fact, Enterprise didn't run on coal, now did it?
No.
You're going to need a bit more power than that. And so a lot of the literature was hoping for an energy source to come along that would allow them to do a lot of what we're talking about. But that's not going to come along anytime soon. Or will it? We realized that we might actually be able to use very small microscopic warp fields to actually facilitate nuclear fusion. So for those of you who are a bit older, you remember Back to the Future, and that's why we got this one where we're going. When he pumps up from Mr. Fusion, he just starts dumping stuff in, and he's producing power, right? There might be a way for us to do that with microscopic warp fields. And for those of you who are a bit younger, there's the arc reactor from the Avengers, because it's basically the same concept. It'll be about the size of two of your fists put together. You can produce possibly about a terawatt of power or so. And
Wow.
you're using hydrogen or something to that effect, right? And here's what we're talking about. There's two types. We've discussed nuclear forces, there's fission and there's fusion. Fission is breaking apart nuclei and making them smaller, which is what we do now in nuclear power reactors and things like that.
Right.
So you take uranium and you break it apart. Fusion is actually forcing them together. The issue with fusion is the fact that when it comes to fusion, we need what we call a brute force approach. We have to slam things into each other because nuclei are all positively charged, and anything that's positively charged repels anything else that's positively charged. So to get them close enough to fuse, you have to make them really hot, and you got to get them really close. That's why the main two approaches for fusion right now are either what we call a tokamak, which is you heat up a bunch of plasma, you spin around really fast, you pressurize it, and everything kind of tries to hit each other, and you're trying to reach a certain critical temperature and pressure to get nuclear fusion. The other way is what Lawrence Livermore did recently, which was they took a bunch of lasers, fired it into a little pellet, and so instantly, or almost instantly, you have this very high temperature spike, this very high pressure spike, and you get fusion as well. There's a lot of force required to overcome this. Yes.
Have they been able to duplicate that anywhere else? Because that's part of the, if you can't duplicate it, it may or may not be real.
So they have not been able to duplicate it anywhere else, but they have duplicated it in Lawrence Livermore. And the interesting thing is they've done it about 6 times.
Oh,
the
very
problem
cool.
with that is the problem with that is that yes, you're getting more power out than you put in, but you can only do it once a month, and you're not getting that much power out of it. You get about the net amount of power that you're getting out. You can boil approximately maybe a quart of water, so you can make some good tea.
And why only once a month? What's up with that?
I'm sorry, say that again.
Why only once a month? Why is it?
One, because you're firing a large amount of energy. 2, because you're actually going back doing diagnostics, see what went right, what went wrong. Just because you can do it once a month does not mean that they were successful the other times. They can probably do it faster, but sometimes they're failing as well, right? They're not doing it consistently. They're doing it enough to actually to show that they can produce a net energy profit. Right. The other issue is that yes, it's a net energy profit. They can't capture that energy. It's not useful energy. You're producing thermal energy. Like again, you're heating up a tea kettle, which is good. And and I don't want to take anything away from this extraordinary accomplishment that they've engaged in, but and it is an important step. But that's a lot of lasers. Everything's got to be lined up just perfect, and there's no way to really harness that yet. So there's no way to engage in power generation with what they've done yet.
Right.
And that's the main issue with that. So those are the main 2 ways. Now there is another way to do fusion, and if you want to, tomorrow, just look up and you'll see it. It's called the sun.
Yes.
The natural way to do fusion is what's called gravity assisted, right? So in essence, every star is a slow fusion bomb. Gravity's pushing everything in. Nuclear fusion is happening, which is pushing back out again. So there's this static equilibrium. I shouldn't say static, a dynamic equilibrium of gravity crunching it and this energy being pushed out. This is why when you get to the end of the life cycle of stars, you actually get these different things. So for instance, our sun, which has 1 solar mass, will get to become a red giant, which means it's going to be burning helium. It's going to expand really, really big because it's that gravity bomb has lost its battle. Supernovas, on the other hand, because they're so massive, they actually crunch so fast that the fusion becomes uncontrollable, and then basically a supernova is in essence a stellar nuclear fusion bomb, and the whole thing explodes. Right? We don't want either of those things.
We got a comment. We got a comment. Cliff says, imagine the power bill they would have to save up.
Yeah, for the Lawrence.
So it's, Lawrence Livermore is actually using so much power. It is actually insane how much power goes into these things. And they've been doing this for about, I think it's been like 20 or 30 years.
Wow.
And again, we're talking about all these lasers, and I think it's like 150 lasers or something like that. And these are not, these are not lecture pointers. These are like, these will fry your hand.
Yeah.
And all of them firing at the same time in the exact same place. It requires an extraordinary amount of precision and accuracy to do it just right. And that's also what I'm talking about with respect to doing it consistently. Every single time they fail, that's just energy that's gone. So going back to the comment, yeah, there's a lot of electricity they're pumping in. They're not getting anything back out of it. They're not.
Well, I think there's data coming out, so
they are getting some research, of course, absolutely, but they're not getting power out of it, which is the point. They're trying. The point of building these things is to produce a reactor that can produce more power than you're putting into it. That's the big holy grail.
Right.
And Lawrence Livermore is nowhere close yet.
Yeah, in fact, being more precise, it's to produce more electricity than you put into.
Yes, very true. Very true. Because just because you're producing X amount of power, heat does not mean you're able to harness that effectively.
Right.
And which is what's happening right now, right? Because you're producing X number of megawatts of power, but you can't capture it. You can't use it. It's being radiated away very, very fast. Which, to use the academic vernacular, sucks. So the third way is gravity assisted. No one does that on Earth right now because, well, the sun's really heavy, and we don't want to do that. That's really, really massive. However, what if we cheat? And so our idea is that we distort space-time on a very, very small scale. We're talking about like nanometers or angstroms or something to that effect. The smaller a warp field is, the smaller the space-time distortion is, the less energy that you need to actually produce the space-time distortion. Now, we've already seen that there's been research done, a lot of theoretical papers have been done, and there's also been an experimental research that was done in 2021 that shows that quantum scale distortions of space-time are practical. You can actually do it. It's going to take a bit of energy, but you can do it. A lot of these are computer simulations. A lot of these were, let's plug the math in, because 2021, where was everybody? At home with their computers because of the pandemic. So a lot of people began plugging these numbers back in and realizing that, no, you can do these things. So our idea was, if you have several of these warp fields set up, you can actually set them up in a configuration where when you turn them on, whatever's inside gets crunched. So it's actually, you start very, very small, very, very small, angstroms, micrometers, something to that effect. Again, the amount of power that you need to warp space-time is equal to the radius. So if you're just doing an angstrom, that's not a lot of power. I mean, do not get me wrong, we're not talking about this isn't 2 car batteries and a bunch of wires. That you can't do this at home. This is going to be like a research lab, don't get me wrong. But it is something that you can reach without having to call the power station and say, we're going to be sucking down a gigawatt of power right now.
Yeah, Cliff goes, they would have to be near a nuclear power station?
No, not for the small one. No, we don't believe so. We don't believe so.
That's an old comment for.
Well, I
for
think
the
he
Lawrence.
was. Yeah, I think he was talking about Lawrence Livermore. But
oh no, they need to. No, they need to be listen, everyone. They need a lot of power, and they're tapping into the grid and pulling a lot of stuff from that. But for us,
they have to do it over time to keep from melting the wires.
Correct. Usually, what they do is they're actually sucking it down and putting it into a capacitor or batteries, and then they're just discharging it all at once.
Right.
Yeah.
So, do you know? Have you worked out what are the requirements to do this for this really small one?
Yes, we have. And when I say we, our team has actually done that. And we're working right now with 3 sets of researchers. One is Dr. Jason Cassaberry. He is a Ph.D. in fusion engineering at the University of Alabama, Huntsville. He's the guy who's helping us kind of design the fusion reactor simulations. Like,
and
once we
get
understand,
him on the show, maybe?
Maybe. I mean, I'll have to ask him. Right now he's teaching, of course, so I don't know if he's got the time, but you can certainly reach out to him, not a problem. He's actually been working with NASA to build fusion rockets. And when we told him what we're doing, he was very excited about what we're doing because he was like, this solves most of our problems. One of the main problems you see with tokamaks is the fact that you're producing gamma radiation, you're producing neutrons. Because those are neutral, you can't control those with the magnetic fields. They just kind of fly out. You're losing energy, which is why you have to keep pumping power into tokamaks to keep them going. Ours doesn't do that. If you're folding space-time, you can literally fold gamma radiation and neutrons back on themselves and redirect their paths, so you don't lose that energy like you would otherwise. And that's one of the main issues that you see with both of the methods that are being used for fusion right now. You're losing power because of contact. You're losing power because of convection. And
And you don't
that's
want it near
not good.
people.
I'm sorry.
And you don't want it near people.
And you don't want near people. And also, theirs are very big. Ours will be the size of a tabletop. So, and we're burning micrograms or milligrams of water, or hydrogen, which will be a lot easier than it was beforehand. So we got Jason Casberry, who's our fusion guy, who's doing the fusion simulations. We've got Dr. Avalio Vasilev and Dr. Nelson Bolivar, who are working on the computational simulations. They're the ones who are checking the math, and they're actually making sure that this is how much energy we think is going to be required, and so on and so forth. Then we got Dr. Chance Glenn, who is actually doing the experimental work. He's actually the one who's calculated how much power he needs, and he's actually using radio frequencies, specifically radio waves, to, in essence, to heat up or to energize what he's calling a warp plasma to actually produce the warping space-time distortion effect.
That sounds amazing.
It gets better. The warp plasma, you would think, is this amazing exotic material. It turns out that he's using ethylene glycol.
Okay.
For those of you who do not know what that is, it's antifreeze.
Yeah. Okay, got it.
Nice. Now, he's calculated how much power he's going to need for that, and he's actually starting his experiments within the next couple of weeks or so. And again, he knows how much power he needs because he did the math. He had the other team with Nelson and Dr. Nelson and Dr. Valio check that as well. And then Jason takes those numbers and puts them into his simulation to figure out the best configuration to produce fusion power. So everyone kind of helps everybody else.
Hey, do you know a Nathan Miracle? He's just joined us. Thanks for joining.
Hi, Nathan.
Very exciting stuff, he says. Excellent.
No, it better be. Whenever I see him, he always walks up and he's like, "How's it going? Tell me how the research is going. What are you doing? What are you doing? What are you doing?"
I love it.
So now you can listen. When it comes to these things, all of them are working together. But Dr. Chance Glenn is the one who's actually in the lab right now. In fact, he just ordered the new materials and the new equipment that he needed. He's actually calibrating that stuff as we speak.
Wow.
And he should be able to be running that in a little bit. In fact, I'm flying out to see him next Saturday because I'm shooting a documentary with him and some other people. And I'm going to look through his lab and play. And I'm hoping he'll let me play in his lab. He might not.
You got to come back and tell us then.
Yeah, especially when you've got the documentary out.
Yeah. Oh no. I will absolutely let you know, and we'll be good to go. Yeah. So our goal right now, our entire goal of the organization is just to show proof of concept that we can do it. We just want to show that we can actually do this in the lab. That's all we need.
Nice.
The idea is, think about James Watt's steam engine. The first one was a piece of crap, but it got the job done. And that's the important thing, right? And the point is, and we all know this, the first generation of any device, it gets the job done, but the second you begin using it, you realize we should cut this off, we shouldn't do this, there's a way to make a better battery.
They're
the
not
goal
usually
is for,
very pretty either.
And they're not, it's not very pretty either, right? But the point is that now we can go back in the lab knowing that it works. Now we can begin figuring out how to cut down the energy requirements, whatever materials that we need, and so on and so forth, right? And so once we show proof of concept, it'll be much easier for us to begin shaving off how much energy is required to do this, right? We need multiple warp bubbles to create sustained nuclear fusion, which I got a great graphic in a second, which I'm going to show, that actually kind of shows you what's going on. But we need to create multiple warp bubbles. That's okay, we can do that. Again, if we can create one in the lab with one setup, we can create 4 with 4 setups, or 6 with 6 setups, or whatever, right?
We got a question.
Yes. What's the question?
Cliff says, not to pry, but who is paying for the research?
That's an excellent question.
Can you tell us?
I can tell you. So we actually have private investors who are investing in us. They signed, for those of you who don't know business, they signed a SAFE, which is basically something of, when we get bigger, you can buy stock from us at a discount, is the idea. We're also bidding on grants from the federal government. So we were actually, in fact, I'm glad that I'm here because we just got this news this week. We were invited to actually present a grant to NSF, the National Science Foundation, for $275,000. So we're actually finishing up the full grant for that. That's phase 1. Phase 2 is $2 million. And we've already been told to get the phase 2 ready because they really are excited about what we're doing. Dr. Glenn has already gotten. I'm sorry?
We got an exclusive. Thank you so much.
You're welcome. Dr. Glenn has already gotten his NSF Phase 1 grant, which is how he was able to get the equipment that he needed. Our goal is, with the other labs, ones we partnered with, we're actually bidding on contracts with different federal agencies to get them started and up and running. The nice thing is that when money comes in from the federal government, everyone all of a sudden believes in you because the federal government really, it's a really bizarre thing about capitalism. No one gives you a dollar until
Yeah.
someone else gives you a dollar, and then they give you
Right.
$20,000. Like, it's really
Right.
bizarre. So we were told to apply to this, and the NSF reached out to us and basically said, please put this in. We turned it in on Monday, and we got a call on Tuesday. Usually it's a month
Wow.
turnaround.
Mm-hmm.
It was 24 hours. And
Nice.
they said, turn this in as fast as you can. We think we can probably have that money within the next 2 months, which would be fantastic.
Bravo.
We're also working on, thank you, we're also working on a NASA grant for the same thing. It'll be $275,000 as well. And that one of them will fund Dr. Valio and Dr. Nelson's lab. One of them will fund Dr. Jason Cassabray's lab. We keep a small amount of it to run ourselves. The rest of it goes there. And then we're raising private capital as well. So that's where the money's coming from, to answer your question. Boy, can I answer that one. Not a problem.
Yeah, there's actually an event next Wednesday for small businesses to talk about working with NASA, but you might already know what you need to know.
My
but get
chief
out
science
there.
officer actually just finished her NASA fellowship. So she
Oh,
actually
cool.
knows who to call and who to talk to. And
Excellent.
Jason has already bid several times on NASA contracts and has won a few of them. So we already know who to go to, who to email, how to fill everything out. We're ready to rock and roll on that.
I'm just thinking for our audience, if anybody else out there has a little project they want this thing on Wednesday, and I have a tab open for that. We'll show in a little bit that you can sign up for. I already signed up for it just to see what it's about. Anyway,
Absolutely.
do you want to get back to your presentation here?
Sure, I guess so.
Okay,
So,
let's do that.
so we want to create and maintain multiple warp bubbles. And here's what's really fun. If you've ever watched Star Trek, you know they're like, let's go warp factor 5, and they say punch it, and then they just go, right? The problem with that is, ironically enough, that's quite inefficient. You're actually warping a great amount of stuff in front of you. The more you warp in front of you, so the more you kind of collapse in front of you and expand behind you, that requires more power. So, when you watch Star Trek and they're like, we're going to go warp 9, and they're like, I don't know if she can take it, Cotton, all that great stuff. The reason is because the power requirements increase a lot, and it's going to take you a lot to get there. So we have a solution to that. Our idea is that you pulse it. You don't actually turn it on a lot. You turn it on so that you're only pulsing a micron at a time. So only moving a micron whenever you turn the warp field on. You just do it 100 million times a second. A micron adds up really fast when you're doing it at that speed. Each time that you cut off this drive, and by the way, when I say cut it off, and I'll show you, there's a graphic that I'm going to show you guys in a minute that kind of walks you through what's going on. You're actually able to get telemetry. So you can actually pick up radio waves and things like that. So you can actually have external communications while you're in the warp field, which is because a lot of the research says there might be an issue with when you turn it on, you cut yourself off from the rest of the space-time continuum. This fixes that. Now you don't have to worry about that anymore. Because the original Alcubierre paper discussed, like, when you cut it on, because you've basically walled yourself off from the space-time continuum, you can't cut it off again. So you're just kind of stuck, right? This fixes that. So, in fact, we actually did a little bit of math. So if you're warping space-time at millimeter per pulse with a frequency of 200 gigahertz, and that's assuming that the warp field, is being cut off half of this time, you're still moving at 0.33 C. That's a third of the speed of light.
Yeah.
That is not FTL. That's not faster than light, but that beats the crap out of everybody else right now.
Mm-hmm.
Yeah.
You can drop stuff into orbit in 6 seconds. You can be on Mars in 10 minutes.
Wow.
So you can literally, go back home and go shopping at Kroger and grab your groceries and come back in half an hour.
And you're not throwing stuff out the back of the vehicle.
It is a reactionless drive. And it's an inertialess drive. So whatever inertial state you're in at the beginning is what you end up at the end.
Which means that you will need some other kind of thruster, because the Earth is moving a whole lot different speed than Mars is.
That's very true. And that's actually one of the nice things about pulsing the drive. I can cut it off and steal gravitational energy where I need to actually catch up with the velocities that I need to.
Mm-hmm.
Not that we've given this any thought.
We did get a couple of comments. Cliff was saying, just glad it's not the Men in Black, the funding he was talking about. And
no, it's not the Men in Black. We're not taking any DOD or defense money for that exact reason.
I think he was talking about, alien influences. Some of the people here are kind of funny sometimes. And then he says, like nuclear pulse drive, little puffs go a long way.
That's very true. That's very true. In fact, that it was partially the inspiration. It was also the inspiration to make sure we don't get cut off from the space-time continuum. So
right, and the fact that you don't have to have big shock absorbers.
Right. Now there are several issues though. Just like you were saying, Jeff. Let's say we cut it on and we go up, 2 miles, and we cut the thing off. Well, there is that. That's it. You just fall like that.
Yeah.
You're no longer cheating, which means you're just going to actually immediately engage in free fall. So if your warp drive drops out and you can't get it, turn it back on again, you turn into chunky salsa.
Yeah, because you're not in orbit.
Right. So we're hoping that one, that won't be the case. 2, we're going to be building multiple nested warp fields. So if one does fail, you'll have another one to have a backup. But 3, we're also looking at using this fusion reactor power to actually produce a fusion rocket as well as a backup, just in case. So that's the solution that we're looking at right now. And here's what's going to look like. And I apologize, this is a 2-dimensional idea. Think of it as a sphere, because it's going to be a sphere. The blue is going to be it might be high energy charge plasma or physical containment, or it might be radio frequencies that are actually putting energy in there. So it might be electrons, might be protons, it might be something of that effect. The purple that you see, in fact, if I can see there we go. If you see that purple there is what's actually holding it in. And when we look at the literature, in essence, what we're seeing is that a warp field is creating a very specific configuration, a geometric configuration of a very small but dense pocket of mass or energy, because E equals mc squared. So it doesn't matter if it's mass and energy. It's a lot of energy, but you can still do it, right? And so when it's on, it's warping. You're warping space-time, and because it's a circle, that means you're warping it what we call symmetrically. It's not moving. You're contracting space-time all the way around it, right? Or expanding it, depending on how you build it, right? Now, here's the beauty of it. To cut it off, I don't need to drain it. All I need to do is decrease the density of the field. I have the same amount of energy inside the field, but because I've made it larger, the density has decreased, which means now the warp field is quote-unquote off. That means I don't have to keep charging the field every single time. So, in essence, I can do this. And that's 100 hertz, that's 100 cycles per second. And the idea is that warp field is turning on and turning off, turning on, turning off, turning on, turning off, over and over again. Now, thermo is a thing, which means that you are going to have some loss from this. You can't keep every electron, every proton, or every energy in there. You're going to have a little bit of leakage. But I'd much rather, for lack of a better term, top off the tank than have to refill the tank every time. If that makes sense.
Yeah.
Now, how this works for fusion? Each of the whites is a miniature warp bubble. When they all turn on, that little piece of blue in the center, you'll see it's getting crunched. So whatever goes into that blue, like deuterium nuclei, become fused. That's how you get a microfusion reactor. And again, because we're talking about, these are like angstroms or microns, or very, very small, I'm burning milligrams of hydrogen. That's nothing. Like, for comparison, if you take if you take I think it's about an ounce of water is about 20 milliliters. That's enough to produce, oh God, almost a gigawatt of power.
Wow.
From that, it's nothing, right? Burning milligrams is nothing. If I'm taking that from water, and it's 20 grams of water, that's going to be like 0.02 grams of, it's 20 decigrams of fuel that you'd get. That's plenty. I can burn that for a while, right? So it goes in, and again, think of it like a 4-stroke engine. So you have like an intake where one of the fields is off, and so that means you've got a way to put stuff in. All the fields turn on. You get your compression phase. Once it's close enough, once everyone's really close, you get basically ignition phase where like the fusion actually happens. That's your power stroke. Then you have the exhaust phase. Because we haven't turned anything off, we haven't let anything go, wash, rinse, repeat. Now, we know that it's going to take a good amount of power to get this thing started. This ain't, again, as I said beforehand, this ain't a battery car. This isn't a car battery. You don't just, stick that in and call it a day. But it's the same concept. You're going to dump a bunch of power in, and the first few cycles of the first few strokes of the cycle of the engine, you're recharging that capacitor or that battery or whatever. But once it's run for X number of seconds or X number of minutes, every single stroke after that is going to be pure profit, energy profit.
Wow.
And the products are going to be helium, because you're getting alpha particles. You're getting a free flow of electrons, and you're getting heat/energy. So what we do is we're going to attach that to a turbine. That's going to heat up some water, just like we've done since the 19th century. It's going to heat up some water, turn something, and you produce electricity. But this is the first power source that I've heard of that actually is going to be producing a direct flow of electrons. So you can literally plug something directly into it without going through a turbine. It will not be the majority of the power, but it'll be a good, decent amount of power that you can actually pull directly from the reaction itself.
And we got a comment. You ready?
Let's go.
Cliff says, I learned about that 50 years ago from the British Interplanetary Society of Pulse Drive, and now it seems we are coming into the technology. And he wrote pulse because it was misspelled.
Typoed. Yeah. But that's cool.
So interesting. Whoops.
Yeah, it's when people were doing the warp drive literature, they just assumed that you just flip the switch and leave the warp field on. Our thought was, why do that? Pulsing is more efficient. You're actually able to aim more effectively, because otherwise, if you just turn the stupid thing on, it's almost a ballistic trajectory. You're just going, and you can't stop it, right? It's almost like the warp drive that was in the early literature was almost like the Star Wars hyperdrive. You're aiming for something, and you're just going to go, and you can't turn in the hyperlane, right? You're just there. You're just going, right? This one allows you to kind of turn more effectively. More questions or comments?
Not this time, but well, I guess I see now because you've got the 4, and is it you think 4 around this?
So we're saying 4. Yeah, we're saying 4 because the tetrahedron, like a little baby pyramid, to the best of our knowledge, is the simplest geometric design that can actually hold something inside of it, if the fields are set up correctly. Now, it might be more. We think that this is the bare minimum that we need. We might need 6 or 8. We're not sure yet. Again, that's where we have Dr. Cassaberry doing the math behind it. For all we know, it might be a cube. You might need 8 vertices to actually make it work. We're not sure yet.
Because if it's a sphere and it's warping everything in the exact same way, when's it going anywhere? Because it's
we don't want it to go anywhere.
Oh no, not for the fusion.
Okay.
Not for the fusion. All right, so there's 2 types of warp fields. One is symmetric. We're talking about symmetric warp fields. Once you turn it on, it's warping everything around it the same way, which means that everything cancels everything out. It doesn't move anywhere.
Okay.
The other one, the Star Trek type, is asymmetric. That's when you turn it on, you contract in the front and you expand in the back.
Okay.
We don't want asymmetric right now. I don't care about asymmetric. We're not there yet. In fact, asymmetric takes more power than symmetric because you're crunching in the front and expanding in the back, right?
Okay.
So right now, all we want to do is just crunch or expand, depending on how the math works out. Either way, as long as we can show we can distort space-time. I don't care if we're expanding one way or contracting one way. Either way, if we're expanding or contracting, we can work the engineering around that, right?
Okay.
We just need to make it work, right? But that's why it's all symmetric. That's all I care about, symmetric right now. That's all we need to show. And symmetric, again, drops the energy requirements, make it easier for us to hit in the lab, right?
Great. Cool.
Now, moving on.
Oh, let me get
Here's
there.
what
Hold
we're
on.
doing.
There you go. Go ahead.
All right. So very simply, what ZC Institute is actually doing is we're collecting money, cutting checks to labs. We're actually we're patenting their technology. In exchange, they're getting money and they're getting equity in the company. We license that technology, but we're also doing a lot of the research as well. And we're pulling in money from several governments. So we're actually pulling in, like I said beforehand, we're actually getting NSF grants. We're looking at NASA grants. We're looking at Department of Energy as well. And before I continue, I do want to say this. We believe that it will probably take 3 to 5 years for us to show proof of concept. Now, Dr. Chance and Dr. Jason and Dr. Valio and Dr. Nelson, I probably should call them by their last names, but whatever. A lot of them are engineers, and engineers are every engineer has watched Star Trek, and they all think they're Scotty. So they all think that if you give them 2 rubber bands and a paper clip, they can build a cloaking device, right? So they're very optimistic, which is good, right? But But the problem is that most of the theoretical physicists are going, no, it's going to take 5, 7, 10, 8 years because we don't know what's going to be wrong. The engineers are going, we can probably do it in 6 months. So I kind of split the difference. I'm like, it'll take us 3 to 5 years.
Got it.
Now we might get lucky. Like the engineers might be right, and I'm hoping they're right. That'd be great. But our budget's planning for 5 years of this, because yeah, you might be able to do it in the lab, but what if there's a heating issue, or what if you need a specific material, or what if you miscalculated and you need another zero on the energy? Like we've kind of taken that into account. So phase 1 for us is collect the money, cut the checks, get out of their way, right? And we're actually looking to add, and I can't say who yet because we haven't signed anything with anybody yet, but we're looking to add on possibly 2 more research institutions to kind of do a different approach. So one of them might be doing like electrical fields, one of them is doing magnetic fields. The idea is that we're going to have 3 labs attempting it. 2 might fail, but 1 won't, right? And one of them might figure out a way to make it easier for another lab to work, right? So our goal is to actually kind of build collaborations between them. In fact, speaking of, we flew them to Atlanta last year, and you'll see here are the names of everybody. We flew them to Atlanta last year and locked them in a room for 3 days in a hotel room. Sorry, a conference room, I should say.
I hope you fed them.
Yeah, sure, whatever.
Okay.
How many came out?
None. Oh, all of them. Yes, all of them. Sorry. No, actually, they were very excited. In fact, I took them out to the last day before everyone flew out. We took them out to dinner, and a lot of them were squinting. I'm like, "What's wrong?" I'm like, "We haven't seen the sun in 3 days." And I'm like, "And are you guys okay with this?" Because they came in on like a Friday night, and the goal was to talk from like 5 until about 9. I was like, "Do you guys want to keep going?" And they're like, "Yeah." 3 in the damn morning, and they're still going.
Yep.
And my staff is just kind of, oh, and we're all just dead. And they're like, do you mind if we finish our presentations tomorrow? I'm like, yeah, because only 2 people presented, and they were talking for 6 hours. So,
I can totally see that.
But the good news is they came in, and Jason, before he walked in, again, the fusion guy, before he walked in, was like, I think there's an 80% chance that we can use this, like these warp fields, to help with fusion. And that Sunday when he walked out, I said, "So what are the chances now?" And he's like, "I'm sold 100%.
Wow.
We can do it. We can do it." And everyone kind of swapped notes of like, "Have you tried this in the lab? Have you tried this piece of equipment? No, don't use that piece of equipment. What about this? Have you checked this math? And have you done that math?" Right? So we think we shaved about 6 to 9 months off of what's needed by putting them in the same room, because these guys are not in the same location. They're all in different places in the United States. But putting them in the same room means they were able to swap that stuff. Because you can talk on Zoom and have like whiteboards and whatnot. It's not the same as actually having the whiteboard next to you and grabbing someone and be like, "Come with me to the board so I can show you the math, or I can show you these things and whatnot," right?
Or someone else, or one of the others walking up to the board that you're working on and going, "Hey, what about this?"
Yeah.
Right. And it's not the same with this. We do try to have like bi-monthly meetings where they come together and meet on Zoom, but it's not the same. We're trying to fly them to Atlanta every 6 months, and I don't want to say locking them in a room, but like locking them in a room.
Okay.
What they and no one complained. No one complained. Like I was like, "Do you guys want to go anywhere?" And they're like, "Well, you said lunch will be outside." "Yeah." "Well, yeah. Do you want to take a break?" "No, we just want to eat. Like, we'll just bring it back in here." And because they're science nerds. Like that's what science people do. They're dorks, and which is great. I want it. So they spent a good, 20 hours, like just knocking through this stuff. So they did a great deal of work here, right? And so we want to fly them back to Atlanta again in like March or April or something like that, and do the same thing again. And this is how the whole thing fits together. So like Dr. Bolivar and Dr. Vasilev are doing all the theoretical mathematical confirmation. They're the ones who are checking the math. Dr. Cassaberry is basically taking the math and taking experimental results and figuring out the best way to apply that to creating a microfusion reactor. And Dr. Glenn is the one who's actually doing the physical hypothesis testing with radio frequencies right now. And all of them together, again, in the center, you've got this increased efficiency because everyone's kind of working on the same thing towards a proof of concept. And you'll see at the bottom, our objective is to create a reproducible nanoscopic or microscopic space-time distortion in the lab. And that's what we're doing right now. With that being said, now let's do the fun stuff. Phase 2, once we show proof of concept, now we begin building fusion reactors. Now we begin doing the research on how to build the fusion reactor. So we can have fusion power within about 10 years if this timeline works out the way that we think it does. Again, these are guesses. We don't know. We're hoping this is what it is. We'll be building, ZC will be building our lab within the next 2 or 3 years. The goal is to actually begin building a main warp lab for us so that we can actually have these guys kind of come in. We still want to have our collaborations, of course, but they're going to have doctoral students and postdoctorates who cannot stay there forever. We'd love to have them come to us, and we want to build up a team of researchers to actually help us with that. So we'll be getting a testing facility. We'll start getting our patents, because that's how we're going to make the money to keep going. So we can license out a lot of that technology, because we don't know who else is going to use this stuff to do God only knows what. This is going to be a whole new field of research.
Yeah.
And we can't even imagine what it's going to be used for. Like, some of the things that we've already thought about are, one, you might be able to get rid of internet lag, because if you set up fiber optic cables with little miniature warp field generators and you time it just right, the photons are going to skip almost like energy skips in your nervous system over myelin sheaths. So now it's going faster. So now it has an effective speed of twice the speed of light, but the photons never go faster than light, because they're actually not going faster than light, are they? Or they're just going at the speed of light. So we might be able to get rid of internet lag. Same thing with computers. If you design computers in such a way where you actually have microscopic warp fields or nanoscopic warp fields where you have a lot of electrons moving, imagine the electrons only having to move a quarter of the distance or a tenth of the distance. Congratulations, you have 10 times the calculation power.
I'm thinking of it for memory, computer memory.
Yep, there's that. I mean, again, there's all kinds of applications that once you put your mind to it, and of course, because we're so deep into it, we're not going to think of half of this stuff.
Yeah.
Which is why we want to license these things out, right? Because we're not going to know the extraordinary stuff that people do with this until we actually, one, do the proof of concept, and two, begin licensing the stuff out, because we don't know. And it's going to be extraordinary. Now, we don't even know if we're going to actually be building the nuclear plant, the fusion plants ourselves. We don't really have the logistics or the supply chain to do that. We might license that out to GE or Honda or somebody else. We don't know yet. Or we might keep it underneath ourselves. We're still kind of loose on that, but we're getting there. That's phase 2. Phase 3. Now that we have fusion power, now that we actually have these microfusion reactors that can produce a great deal of power, now I can begin making these warp fields bigger. So now I can go from micrometers to millimeters to centimeters to meters.
Oops.
Now I can put stuff in this thing. With a meter, I can put a drone in there.
Yeah.
With a meter, I can put stuff in there. If it's 10 meters, that's a car. And in essence, just to show you what we're thinking about, something like this. Imagine being able to get into your, and we'll call it a TARDIS. I totally made that up. Not sure I've ever heard that before. You get in Atlanta or New York or wherever you are, and you say, I want to be in Nairobi, Kenya. And the computer says, what address? You give it an address. And by the way, we've already figured out, if you want to hear the sound and the light blinking, we can do that too. 4 seconds later, you can pop open the police door and you're in Nairobi. Because the goal is that because it's macroscopic, you can literally go up, curve over, come back in about 4 seconds. Because remember, you're moving at a tenth the speed of light. So 4 seconds is actually plenty of time to go where you want to go. Now, there are some issues with that right now. One of the issues that we're looking at is warping in an atmosphere might create a plasma shock wave in front of us. So we have to figure out how fast you can go, quote unquote, how fast you can move before you do have a plasma shock wave in front of you, right? We don't know what that's going to be, which is why we have to have the lab, right? We might have a multi-gear analysis. We might have like a TARDIS that has gears, one for like, planetary atmosphere and one for interstellar, one for space and then one for like deep vacuum space, right? We don't know yet. But we do know that we're going to actually have some issues in that regard. But because we're only warping things at like a micron at a time, again, go back to the TARDIS doesn't have a liftoff. It doesn't have a landing need.
Right.
It just kind of goes. Ours will be the same way. If you're only warping a micron at a time, you can launch from grass and not hurt the grass. and land on pavement. So you don't need airports anymore. You don't need anything of that nature. You can
Wow.
literally just get in and be wherever you want to be in 4 seconds. So actually, it's like Star Trek's transporters, but better because there's no Tom Riker. There's no duplication. There's no people getting, beamed up and turned into soup. There's no Tuvix where people get combined. None of that crap. You just get in and you go. I mean, 4 seconds is actually faster than a transporter. Transporter takes 7 seconds. Not that I know that off the top of my head. So our idea, and again, going back here, I have not discussed faster than light travel yet, have I?
No.
Not touching that yet. This gives us the ability to understand how the warp fields work, how we nest them, how we build them, and even better, I don't have to put in this extra energy to get to FTL. I don't need it yet. I don't need faster than light travel right now to go to Nairobi. A tenth the speed of light, though, does make every rocket ship obsolete, right?
Yep.
And again, being on Mars in 8 minutes, I mean, suck it, Elon.
This sounds safer, too, because rockets blow up.
Yes, and that's the nice thing about fusion reactors. When they stop working, they just stop. There is no overload. There's no way to actually make it overload or anything else of that nature. That's just it.
Okay.
Yeah, the most vulnerable thing would be the capacitors.
And that's the nice thing about it, too. By this point, we've probably minimized the energy requirement, so even the capacitors will not be this massive amount of power that you need, right? That's the goal. And that's the wonderful thing about it, too. If it's done correctly, you could build that into the walls of the TARDIS, you might not need as much power. And again, that's the whole point of it, right? Like the other example I usually use is transistors from the 40s. Like when Intel first patented the transistors, this big, massive thing, and it could do calculations, and that's great. But now you can fit billions of them on a chip, right?
Yep.
Our idea is the same way. We're gonna make it more efficient, not just from a space perspective, like a volume perspective, but also from an energy perspective. We're gonna make it more energy efficient. So we won't need as much of that capacitor power as you would beforehand. Because remember,
we got some comments. You got a second?
Let's roll. Absolutely.
Right, Scott, he says traveling at FTL speeds does not scare me as much as the instant stopping.
But you're not moving, are you, Scott?
No.
Yeah.
Not this. Cliff also
the universe
says,
is moving around you.
Yeah. Cliff also goes, or valves sticking.
Yes. And that's the other thing too. At this, and this is where it gets fun. Now we're no longer discussing theory. Now we're discussing engineering and technical challenges.
Right.
And that's the fun thing, because by this point, we've actually done a lot of that research of, will valves freeze up? What happens when a valve ends up in the warp field itself? Or what happens with X, Y, or Z? Like, we're going to face most of those things before we actually begin launching these macroscopic things. So by the time we get there, we've done most of that quality control, error checking, things of that nature. Because we're gonna find out a lot of that stuff. That's why, by the way, phase 3 is about 10 years, because we're not going to fly anybody until we've done every single test that we possibly can to see what all can go wrong and how we're gonna program this or set or design it in a way where, I don't want to say foolproof because there's no such thing, but make it as safe as we possibly can given the technology that we're using. But yeah.
Yeah, I keep thinking about sticking the landing. Say you're going from here to Nairobi. You're at different velocities at different points on the Earth.
That's very true, which is why one of the things we'll be doing during phase 3 is producing a partially computerized navigation system that will use transponders to ensure that you're keeping up with everything. And again, remember that because you're pulsing it, every single time you turn it off, guess what you're getting? New telemetry data.
Right.
And remember, because it's not a rocket, there's no vectors. So I can literally, for one pulse, I can go up, and then I can go to the left, or I can go to the right, or I can go back down again, right? So you have such exquisite control over what you're doing.
Wow.
That every single pulse, again, you're getting new data. So you're getting confirmation of where you're going and what you're doing 100 million times a second.
Right.
So
I'm just thinking that you need to manage your internal momentum, because when you go from one velocity begin state to a different velocity end state,
so that's where it gets fun.
It's sticking the landing.
Well, that's where it gets fun. Remember that, and this is why computers are so great. The calculations have been done. All you have to do is figure out a way to either pick up velocity or bleed it off. Guess what you can do? Cut off the warp field.
Right. Yeah.
Now you're picking up gravitational energy. You're
Right.
falling a little bit, which means you can match velocity, and now you just go the rest of the way.
Can you rotate in the warp field?
Absolutely. Maybe. Don't know yet.
Because that would be a way to alter your velocity.
But what you can do is, again, each time that you use the warp pulse, you can go left or right. Like you're not bound by any kind of vectors. You're not bound by any kind of velocity. So you can kind of, you can kind of go this way and then cut off. So now you're falling at a specific thing. And I see what you're saying with respect to that, because then you're adding a horizontal component when you're actually dropping. Possibly, I don't know yet. We can probably do it. And again, because we're in phase 3 right now, this is all speculative, because until we know the physical properties of the bubble itself, I can't answer that question.
Yeah.
But more than likely, we're not going to be using one warp field. We're going to be using multiple ones, which means that we'll be able to possibly do it in such a way where you are able to actually rotate it inside, or we can just throw a booster on it and rotate it anyways. We can use normal physics to actually do the rotation if that's required. And remember, we have something that's producing exhaust. That's the fusion reactor.
Right.
So there is a way to actually produce rotational a rotation inside the warp field if necessary. To the best of my knowledge, do not quote me on this. I am not a scientist like that.
Will the computers be able to keep up? Because this sounds like a lot of calculations all at once, and that was one of the problems with landing on the moon, was that the computer was overcome by the amount of data. We
have to remember that we have smartphones right now that have more computing power than the entire U.S. space program combined.
Yep.
It is extraordinary.
I get that.
Much computing power.
You're talking about something very, very... It sounds like it needs lots of computing power.
Not to me.
Okay. All right.
Not to me.
I would say that here's the thing. You might both be right. You might both be wrong. But given the number of variables in question, it doesn't seem that it's going to be impossible, especially given how computing technology is working right now.
Oh yeah.
I don't see it as an issue as of yet. It might be, and that's why we're also going to have I don't want to say hub. Well, I guess I am going to say hubs, navigation hubs. We're going to actually run a navigation system where we have people actually overlooking the AI as well, because any system that doesn't have people in it is going to cause problems. But you will be able to run it in such a way that's mostly autonomous, and there will be a way to actually set up a navigation system that takes care of most of this stuff. And you only call to the hub when you have a problem, would be the idea, right?
Got another comment. You ready?
Yeah.
I don't quite understand this, but isn't China or Taiwan? Maybe don't they have a fusion reactor that just ran for 20 seconds last year?
They did have a fusion reactor that ran for 20 seconds. They absolutely did. It did not produce a net profit of energy. That was the issue. They ran it for a while. Yes, they certainly did. But they had to put more energy in than they got out. And that's not an engine. That's a heat sink. Yeah. It's closer than they got before. And running for 20 seconds is good, but they were not able to reach net energy profit. That was the main issue with it. But running it for 20 seconds was fantastic, because a lot of what we see right now in the United States and in Western Europe, they're running it for 5 seconds or 3 seconds or whatever. And they're producing power, but the longer you can keep it on, the more fusion reactions you're going to get, and the better you're going to have a chance to get into energy profitability. But they have not reached energy profitability yet in that regard. Yeah. To the best of my knowledge.
Yeah.
And just thinking about the configuration of the warp fields to produce the fusion, are you thinking of arraying them? Because it seems to me that you could use 2 of them in the next set, because they're all expanding. They're expanding symmetrically. So
there might be a way to set them up that way, but our thinking actually was to have a set of 4 or a set of 8. Mm-hmm. You start the first one. The first one recharges its first batteries. That one provides the energy for the second one. Second one starts, you recharge the energy, the batteries twice the power. And so in essence, you basically get the 8 reactors starting up. Now I have 8 times the power that I need. Right. And now I can really warp some stuff up. Whether we can build the reactors to basically create a double reactor in that regard, I don't know yet. That's Jason's job, not mine. But you might be right. I don't know yet. And again, at this point, we're in speculation, because we don't know how the warp fields are going to look. We don't know what the machine's going to be to produce that bubble, right? But with that being said, the sky's the limit in that regard, right? We don't know what's going to happen in that regard. You're not wrong though. We've thought about, do we daisy chain them, right? For lack of a better term. do we nest the warp bubbles so that you can burn other things? In fact, one of the things we're thinking about is as we start doing this stuff, we can begin burning not just hydrogen. We can burn helium. We could burn lithium, beryllium. If you remember when you saw Doc Brown, let's go back way back here.
With the
So you
banana
see
peel.
Doc Brown, the banana peel, he's dumping in, he dumps in beer, right?
Yes.
That's all organic stuff. So that's carbon, nitrogen, oxygen, and hydrogen, right? As long as it's above iron on the periodic table, you can fuse it and get a net profit of power out of it.
Right.
So here's what gets really fun. That means we can go to landfills and dig up plastic and burn plastic
What I
and get
tell
rid of
you.
all that plastic. And now and again, of course, are we producing any carbon? Nope. This is zero carbon emissions. So we can go and dig up plastic and actually take care of our plastic problem at the same time we're producing unlimited power.
Yeah. You have to be careful about the fusion product, though, because you might not be producing carbon, but you smack a couple of carbons into each other. What do you get?
Well, see, it's funny you should say that. So one of the side projects we do want to keep under the ZC umbrella, we call it Alchemy Inc. Because you're absolutely right. You slam two carbons together, so 6 plus 6 is 12. So that's going to be nitrogen. I can't remember off the top of my head. It's going to be one after sodium, magnesium. It'll be magnesium, right? So if we need molybdenum or we need praseodymium or whatever, we can just bang it together in the alchemy lab, right? Now it might be that we can't. It will not be a net energy profit. It'll probably be, you'll have to put more power in than you got out, but we can engage in transmutation. And to go back to your point, we could produce several reactors that do burn carbon, but they're producing, I don't know, sodium chloride, or something that's not too terribly terrible, right? Like we don't want to do that. And it might be that the fusion reactor that we have at the beginning, the one that I just showed you guys, the tetrahedron, it might just be that just like with the TARDIS, you have multiple gears. I need burn carbon, so we'll just put it in gear 3, and we'll just burn carbon. We don't know yet. The goal is to make it as simple as possible and also make it as safe as possible. So if we are burning plastic, we don't want to produce, I don't know, technetium or something radioactive. We want to produce something that it comes out that is either A, useful, or B, not unuseful.
Right.
Or that's neutral.
It's not a good byproduct.
No, it's not. Which is why we're going to have a lab that's actually going to be working through all this stuff, because it's we've already thought about the possibilities and the potential of this, because you're absolutely right. You could do all kinds of crazy things with it, but we don't want to produce something that's like, oh, and by the way, it produces enough gamma radiation to make you the Hulk. Like that's not something we're down for, right? So the goal is to make it as safe as possible. And you might have 20 different pathways to make what you want from plastic, but only 2 of them actually produce something that isn't radioactive or isn't revolting or isn't poisonous, right? And we'll figure that out before we even produce anything is the goal. That'd be the hope, at least.
Amazing.
Yeah, so that's what we thought about with respect to that. Now we get to the really fun part.
You got more slides, right?
Yep, just a few more.
All right, let's go for it.
Phase 4.
Last but not least, now I'm 70-something by this point. But now that we've really figured out how sublight warp ships work, which, by the way, with sublight warp ships, we can colonize the solar system with sublight. It's not a problem. So Mars, you can put up stuff into orbital platforms. You can start mining the asteroid belt. We can make the expanse without the crap. But
haven't seen it yet.
it is fantastic from a hard sci-fi perspective. It's amazing. It's great stuff.
I've heard.
And there's a lot of curtsing, so I was very excited. But now that we understand how sublight warp engines work, we can begin working towards FTL now. And we don't think that it's going to be this massive barrier. We think it's more like what Chuck Yeager dealt with as an engineering and technical challenge. When he actually broke the sound barrier in the Bell X-1, when he reported back, when he radioed back, he basically said something to the effect of, the instruments have gone all wonky. They've gone all weird, because he was breaking Mach 1, right? Because he had a sonic boom and he broke the sound barrier. We think that it's not going to be like this magic mystical barrier. It's just we're warping at 0.99, and after we juice it a bit more, we're doing 1.01. Because it's not really this magical barrier if we're warping space-time now, is it? And if that's the case, That means we can do FTL just by doing what we're doing now. We can make it just more efficient. In essence, we want to drop power requirements. We want to make the warp field more efficient.
Yep.
And we want to be able to get more pulses per second. Because the more pulses you get, the faster you're going, right?
Hey, Nathan says, I love that the goal is FTL travel on first contact day.
You mean that?
Yeah.
And actually, it's the day before first contact day because I want to beat Star Trek.
Oh, when is that?
Well,
April the 5th, 2063.
well,
It's
the
first contact
Vulcans
day.
need to know when to be there.
Yes, that's true. That's very true. But the goal is to actually do it on the day before Zephyr Cochrane did it in the fictional universe. And we think that if we can hit this correctly, we can do this. And even better, we don't need, in Star Trek, they use matter-antimatter for the power source, right?
Mhm.
We don't need that. We can use fusion reactors for that instead. So we can probably
Nice.
build the Phoenix within my lifetime.
Yeah.
Wow.
Because I
Is that what it was
all,
called? Is that from Cochrane's called the Phoenix?
That's the Phoenix. That's what
I
he.
remember
That's
the
what,
music.
yeah, that's it.
I remember the music, the Steppenwolf's Magic Carpet Ride.
well, I've never considered antimatter as a fuel, but as a battery.
Yes,
Because
but
you have
the
to
thing.
use a bunch of energy to make it.
Yeah.
Well, yes, but the thing is that it's still a fuel because I see the analogy of where you're going, but yes, you're using a lot of power to make it, but you can't make it out in space. So it's still a fuel because you need to load up whatever. But the nice thing is our fuel's water.
Mm-hmm.
So and I didn't say fresh water.
Right.
You can just literally throw a big, massive tube into the ocean, and you can use a desalinization plant to get fresh water. Now, the issue with that
You
is,
don't even need that.
well, no, but I want to do that, and here's why. One of the issues with desalinization plants is the fact that they're very energy intensive, right?
Right.
Well, now I don't care. I've got fusion power. I got energy to burn. That's
Yep.
not an issue, right? So no big deal. Who cares? The other thing is, climate change is happening right now. I can refill the Colorado River. Like we can start pumping out tens of thousands of gallons of fresh water without an issue because I don't need a lot of the water to run my fusion reactors. So I can produce fresh water by the kiloton if I want to, and we can re-irrigate the planet.
Mm-hmm.
So this solves climate change. This solves the fresh water crisis. This solves the energy crisis.
Mm-hmm.
Wow.
We become a Kardashev 1 civilization. I think that's everything. Yep, I'm done.
Hey, Cliff goes, we don't have the time for the time. What?
I don't know what you mean, Cliff.
Oh, we don't have time for the time. It's a primitive culture, and she's trying to blend in. He'll get it.
Okay.
Deanna Troy is drunk in First Contact, and she's discussing the fact we don't have time to argue about time. There's no time, and she discusses the fact that it's a primitive culture, and she had to take 3 shots of something called tequila to get Zephyr Cochrane to talk to her. And she talks to Riker, and she's like, "Listen, it's a primitive culture. I'm just trying to blend in." And he says, "Oh, you're blended, all right." Which is where he was going with that.
Okay.
God, I think I missed that. All right. And you had
It was worth ticket price alone to watch Deanna Troy get smashed.
Cliff comes back with.
Yeah, he got it.
Yeah.
Good.
Yeah, I had some questions, but I think we've already covered them. Yeah.
And you mentioned some things we should do, but I think we covered that too, right? Yeah.
I think so.
Excellent. Oh my God. So amazing. I can't wait to hear more. I mean, as you go along, you got to come back and tell us what's happening.
I'll be happy to. It'll be great. It's exciting on my end as well because I get to see this thing that was science fiction not even 10 years ago. And now all of a sudden there's a decent chance we can actually turn it into something real and something that's not just real, but useful, something that we can actually do with it, something that can do some real good in this world. So yeah, I'm excited about it. I get to wake up every morning and check my email and I get to go, what next? What's going to happen now? This is fun.
Nice. I love it. All right. Well, we're going to watch for some more comments and questions from people in the audience. We do have a couple short segments left, and stick around, Greg, if you don't mind. If we get questions, we want some help answering them because I'm just riding your coattails, hanging on for desperate, just dear life. Like But you do make it very understandable. And here we have a question right now. Janie Becker, fascinating and fun, exciting possibilities. Thanks. Please keep in touch. All right.
Okay.
You want to do your part?
Yeah. So some stellar events this week, January 12th through January 19th. January 12th, Mercury is at the greatest western elongation at 24 degrees. You can look for Mercury very early in the morning in the east, which means, yeah, not likely for me, before the sun rises. The two inferior planets, that'd be Venus and Mercury,
Yep.
are always near the sun from our perspective here on Earth. Yeah.
Yep.
January 13th, Moon is at perigee. January 14th, Saturn and the Moon are in conjunction. January 15th, Neptune and the Moon are in conjunction, and U.S.
We celebrate.
celebrates. That word was just gone for me. Martin Luther King Jr.'s birthday. January 16th, Moon is on the equator, balancing just right. January 17th, first quarter moon, and the moon is at ascending node. January 18th, Jupiter and the moon are in conjunction. January 19th, our Friday night show, and we're planning on another profile. Want to know who? Stick around. Find us Fridays at 9 p.m. Pacific time on Everyday Spacer Facebook page and the Everyday Spacer YouTube channel. And Uranus and the moon are in conjunction.
What inspires you the most for the coming week? Oh, we got a comment. Cliff says rockets landing on their ass was sci-fi only before Elon.
Yeah.
No,
There was a DCX, but
the DCX, of course, you know,
but
the
it was
X is
experimental.
all right, so I usually do a pretty good segment of other events and activities, but I'm going to go and just show you the one thing we talked about. Let's see, where was it? Do you remember what we talked about? Because this has gone long, and I know it's late for you, Greg. When is it?
When you're ready.
Yeah, I don't know which one it is. What did I say?
No worries. I plan to stay up late tonight anyways.
Okay, well,
Always working, right?
but bunches of things for the solar eclipse.
Well, this is the one I was talking about.
Okay,
So go ahead and
here,
share.
Let's share this.
Yeah. So if anyone in our audience wants to learn more about how NASA works in terms of small businesses, and I actually signed up for this one, so I'm going to tune in on the 17th. For me, it's going to be 10 a.m. I think it is 10. I'm sure what. Yep. But here you go. It's an Eventbrite event, and you can learn how to. This is a learning series, resources to help you do business with the federal government. So that's pretty exciting for me. Anyway, that's good because, like I said, we're running pretty late, and we've shown all these before. All right, so let's see.
I apologize for going so long. It's not the easiest subjects to discuss.
It's great, and we're very excited to hear from you, and we loved it very much. I just don't want to keep everybody up really late.
Well, one of our shows was 2 hours long, so
Yes.
we don't want to do that.
Oh, that's a lot.
Yeah. And we've shown these slides. I set the tabs up and I've shown them before. But yeah, you can put your name on different vehicles, and there's a lot of fun stuff to do out there. So let's go to this part and we'll watch for more comments. Oh, Janie says applause. Thank you.
Okay.
She's one of our biggest fans.
Yeah. If you or someone you know has done something interesting involving space exploration, science, or astronomy, we'd love to share our live. Join us again next Friday, January 19th. The profile we're planning is about Dr. Gerald K. O'Neill. Gerard. Yes. I said it right every single other time. We saw the High Frontier on Curiosity Stream recently. And
so amazing.
And which inspired this profile episode. So tune in next week and learn more.
All right. Anything else from you, Greg?
No, I think I've covered quite a bit right now. And again, thank you, Pam. Thank you, Jeff, for allowing me to come on. I really appreciate it. And thank you, audience, for the excellent comments and the questions that you had. And I hope I was able to answer everything as effective as I could, considering the fact that this is a very speculative technology that we're not sure how it all works yet.
Right. You don't have the answers yet, but you have the way to find the answers.
That's what good science is.
Yeah.
Absolutely. So thanks, Cliff, for that. And anything else from you?
No,
I think
that'll
I'm
do it.
good. Yeah, definitely come back, Greg. And if anyone else on your team wants to join us, we would love to hear from other perspectives from your group.
Absolutely.
So, all right, stick around a second, and thanks, folks. We'll see you next week. Good night.
Thanks a lot, everyone.
Yeah, good night.